There's not any juice over there? No, they've been shorting us on juice and giving us fruit instead.
You can have mine. You can have mine. I don't even know if I
mean, that's okay. I can pull it up.
No, I just wanted to take mine. But I really want to know how many I got wrong. I did it at 9:29 this morning.
All right, which one? Starting with linear? I thought we did linear together. Are you just talking about the characteristics? All right, so linear. We have 0, 0, 1, 1, negative 1, negative 1, and we have a line that looks like this. What's the domain? Negative infinity to infinity. What's the range? Negative infinity to infinity. What else did it ask? Intercept. What's the x-intercept? 0. What's the y-intercept? 0. What's the maximum number of roots or zeros? In other words, no matter how you twist it, turn it, or shape it, what's the most number of times it could cross the x-axis? 1. It'll never cross more than 1, right?
I don't really know.
Okay. How about in behavior? As x approaches, what do we start with? As x approaches negative infinity, what does the graph do? Up or down? Down. That means on the left side, I go down. Now, Hank and Charlie, y'all are going to be the first ones complaining that you don't know how to do that.
No, I did
Where's your sheet?
I did pretty well last night, though. I can't lie.
Where's your sheet, though?
Oh, I my book bag.
How about as x approaches positive infinity? It goes up. Continuous or not? Continuous. Why? All of them are. Why? What does it mean to be continuous? You don't, that's right. You don't have to lift up your pencil to draw the graph. This, as x goes to negative infinity, that means the left side of the graph. If it goes up, you do positive. If it goes down, you do negative. And then as x goes to positive, that means the right side of the graph. All right. What else on your homework? Cubic. Cubic. 0, 0, 1, 1. Negative 1, negative 1. So we did the graph together yesterday. What's the domain? There you go. What about the range? Same thing. What else did we ask for? X-intercept. 0. Y-intercept. What is the most number of times that this graph could cross the x-axis? The way it sits now is 1. Yes. We'll talk about some ways that that might change for this one, but yes, 1 the way it is now. How about in behavior? As x approaches negative infinity, what does f of x do? Down, negative infinity. That says the left side is going down. How about as x approaches positive infinity? That's right, it goes up. And of course, continuous. If you flip over and look at the square root, I do want to tell you about one little thing that I forgot to mention yesterday. Because the square root is a little bit different, and it goes 0, 0, 1, 1. We said we could go out to 4, 2, but it looks like this. When I'm talking about in behavior here, I can go to infinity, right? Because I have that right end. Goes up. But on the left side, I never go to negative infinity. In fact, the furthest left my x goes is what? 0. So I say as x goes to 0, what does f of x go to? 0. So if you ever just have a point that you into, that point is an in behavior there. The range here would be from 0 to infinity. Domain's the same thing. So left to right, the furthest left it goes is 0. The furthest down it goes is 0. Yeah. Cubed root, which looks like this. Yes. Here's my cubed root, right? So domain here is everything. How about the range? Anybody? Somebody, anybody, everybody? Well, look from the bottom up. What's the lowest the graph ever goes? Negative infinity. This is, see how this is kind of inching down and inching up? And it goes left forever and right forever?
That's not a matter of just going up.
Well, because this is not just a straight line going across. This is like it's going up and across at the same time. So it's not going up very fast, but it's going up nonetheless. Go to your seat, or I'm gonna call Teresa. No. Okay. Keep moving, Logan. Keep moving. X-intercept. Y-intercept. Anybody? 0. 0. Maximum number of roots or zeros? 1. In behavior, as x approaches negative infinity. Keep going, Logan. What does f of x do? Negative infinity. It's going down. Keep moving, Logan. As x approaches positive infinity, f of x does what? Infinity. It goes up. Keep moving. Keep moving. All right. I have the attention. All right. You have technically heard this before, done this before. I'm going to pass you a little green sheet too, and we'll talk about it in a minute, but I want you to go ahead and get one. Do not lose this. I do not have a bunch of extras of these to give you, and there may become a time, or there may come a time on a test or a quiz. I'm no promises, so don't start saying you can, but there may come a time when I say, okay, you can use your little green sheet, and that's it. And if you don't have your little green sheet, well then you're SOL. So make sure you keep up with your little green sheet. That's why I can color text. All right, so while that's coming to you, let me talk about transformations. You have technically done this before, but you may or may not remember it. Do y'all remember we talked about that, sliding, shrinking, stretching, flipping, all that good stuff? All right, so that's what we're going to do. I will probably give you your what's today? Tuesday? I'll probably give you your project on maybe tomorrow. Probably until I'll give you at least over the break. I don't know when it's gonna be. It's up to you. I don't ever do a notebook check. Yeah, when I give it to you, I will. When I give it to you. No, not now, because you don't have it now. It wouldn't make any sense because you don't know how to do it yet. All right, ready, Freddies? I think that today I will run you through all of them, but we will just practice with some of them. I'm also going to give you a packet. The packet will be due at the conclusion of the unit. So you'll have certain numbers through the packet every day we move through. All right, so here's what I'm going to do. I'm just going to transform a parent graph today, right now as I introduce this, so that you can see what happens, okay? And in fact, if you look at the left side of your little sheet, I didn't really run it for the left side. I ran it so you'd have this little guide over here on the right, but whatever. It says that we're using the absolute value parent function as an example. So I'm going to put this absolute value parent function. All right. If you look at the first equation, and we've kind of already made this connection, so I hope you can see this. If you were to graph f of x equals the absolute value of x plus 2, where's the vertex on this one? Somebody. The red equation over here. Where is the vertex? It's what? -2, 0, right? I got to change that sign. So -2, 0. And then I do my slope up 1 over 1, up 1 over 1. What has happened between the blue graph and the red? It just shifted over, right? Every single point has just shifted which way? How many? 2 spaces. Okay. That's what's happened. Does everybody see that? What if I changed it to now what's my vertex? Vertex is now 2, 0. Same thing, slope of 1. Okay, no. Okay, so, yes, that's exactly what it is. So I want you to make a conclusion here. If I add something to the x or subtract something, what is going on? What is happening? It's moving left to right. That's exactly right. So if you look over on the right side, the very first line on your table there says f of x plus h. This moves it to the left, h, and f of x minus h moves me to the right, h. Does it make sense why, if I say that? This does not just apply to absolute values. This is any parent function, okay? So if I had, let's say, what do you think has happened here? What's the parent function, first of all? The parent is that square root, right? So I have to understand what the parent looks like. The parent starts at 0, 0, 1, 1, and goes off this way. What does this graph then look like? It moves everything to the right 1 space. So this graph, instead of 0, 0, moves to the right 1. That point moves to the right 1. This is the graph of x minus 1. It just moves it right 1. Anything in the world, it's just moving it to the right that many units. Does that make sense? Look at your little green cheat sheet. And this is going to be the third line down, not the We did it in a little bit different order. You see that line says f of x plus c? Yes, Miss McGee. Or f of x minus c. It tells you those are horizontal translations. Translations just mean slide. If it's adding, you move left. If it's subtracting, you move right. And then you got, I call this, where that column that says change, I call this a cheat code. And here's why I call this a cheat code. You take the parent graph. The XY is the parent, or what you started with, right? So let's look at the translation. This is a translation right. So it says take XY and make it X plus C, but keep Y the same. That means every point on the parent graph, this point was 0, 0. This point was 1, 1. It says take that point, add the C value to X, but keep Y the same. And I know that this seems it seems like I'm way overcomplicating this, but you need to understand the way these little cheat codes work, because when we get to dilations, it's going to be difficult. Okay? So here, 0, 0 becomes, well, my C value, remember, is 1. So 0, 0 becomes 0 plus 1, 0, or 1, 0. Here's the 1, 0. Does that make sense? You're just adding that C value to every X, keeping Y the same. All right, that's translations. So your second line there, did we fill out the second, or we just did the first? Yeah, we did that. All right, let's look at, I'm on the left side now with numbers 3 and 4. Number 3 says f of x equals the absolute value of x plus 2. And I'm gonna come over here and I'm just gonna draw my parent graph. Just so you can see how it's changed. Looking at this one, what's the vertex? What's the vertex of the blue one? 0, 2. It's got a slope of 1, so up 1 over 1. What happened? It moved up 2. How about if I did f of x is the absolute value of x minus 2? It goes down 2. Same graph, it's just been slid up or down. Does that make sense? So back to the transformation guide. If you have f of x plus k, what does that mean is happening? It goes up, okay. And if you have f of x minus k, what do you think that means? Down k. Again, on your green cheat sheet, it's the first 2 lines on there. Okay, it's only impacting the y values, not the x. All right, let's look at 5 and 6. Actually, let's skip down to 7 first, then I'll come back to 5 and 6. We have. It's just impacting the slope. We did it with quadratics. I'm showing you with absolute value, but understand this works for any parent function. And how many parent functions did you learn so far? 6? Was it 6 or 7? I think it was 7. Okay. But we'll be transforming all of those. And in fact, it doesn't matter what the function is. As long as you do this, it slides it and shifts it and does everything else. All right, let me do my parent here. Yes, because translations, think back to geometry. Translation means slide. Huh? No, I'm about to do number 7.
Wait, so are we going to graph this every time?
You're going to graph, you won't necessarily graph the parent every time, but you will graph each function, yes. Oh no, I got a packet for you. Yeah. What's the vertex of this one? Look at it again. Look at of the blue one. What's the vertex? 0, 0. It's still 0, 0. The H and K are not there, right? The only difference in this one and the parent is the slope is -1 instead of +1. So I go down 1 over 1 instead of up 1 over 1. What does it look like has happened to this graph? It flipped. What do we call that in geometry words? It reflected, right? It reflected over the x-axis. That's exactly right. If the x-axis was a mirror, then it would that's where it would be reflected down there below it, right? Does that make sense? So my question to you, let's see if you remember this from geometry. How do you reflect points over the x-axis? You're close. You're really close, actually. Every point that I have to reflect it over the x-axis means that I would keep the x the same and I change the sign on the y. And look at this, it makes sense. This point was 1, 1. Whenever I reflected it, it became 1, -1, right? This point was -1, 1. Whenever I reflected it, it became -1, -1. Does that make sense? All right. So on your sheet, on your guide here, negative f of x. So if you just throw a negative in front, that means it reflects over x. Now I do want you to add one other thing here, and that's f of negative x. In other words, if you just make the x negative, that's exactly right. It reflects over y instead. Add this as another piece in that very last row. For this one, it wouldn't. Why wouldn't it? And it's already symmetrical about y, right? Well, think about even if I reflected that over y, it'd flip, right? So this point would be over here. This point would be over here. So I could still reflect that over y. The square root could, yeah. Those are the easy ones. Is everybody okay? Y'all ready to do dilations? We've kind of already done them whenever we talked about square roots. It's the figuring out what they do. So I'm not going to throw dilations on you today, but I do like to practice with. But I do want your chart filled out. What? that might have been why you were on your phone. All right. If I graph this, what's different in the parent and this one? So 0, 0, let me put the parent on here so you see. Here's my parent, rough sketch. What's the difference now? What's the vertex? 0, 0. But now it has a slope of 2. 1, 2 over 1. Reflect. What happened? Change the slope. It got skinnier, right? Now, I want you to think about this for just a second. I'm going to call this, when you have a number in front of the entire equation, I called it a dilation, okay? And we see that this graph got skinnier. You agree with that? Okay. I'm going to call this a vertical dilation, but if I did, so if I thought about it being vertical, I'm going to call this a vertical stretch. Would you understand why? Okay, if my y-axis was made out of rubber and I could stretch it out, what would happen to that graph as I continued to stretch it out this way? It would get skinnier and taller, right? And that's exactly what's happening. That's why we call it a vertical stretch, okay? So this happens when A is bigger than 1. But what happens if A is smaller than 1? It gets wider because I'm squishing it down. I call this a vertical shrink, or sometimes I can call it a vertical compression. Yes, kind of, but we didn't use this terminology. But this is different than what I did with the parabolas. Well, a little bit. Either one. You can use whichever one, but some, if you see it written either way, be able to recognize what it is they're asking. But you can write it either way. I generally tend to say shrink.
Like what we did with parabola, right?
Okay. Now there's 2 more types of dilations I need to add on here. Okay. This time, if your A is hooked to the X, okay? So in other words, instead of it looking like this, it might look like this, okay? This is the difference in a vertical and a horizontal. This is a horizontal dilation. And everything with X is always opposite. So here, if A is bigger than 1, and I should say the absolute value of A on all of these. If you don't understand the dilations today, it is okay. And once you have the information, then we're going to practice with it and it'll start coming together for you. But as A gets bigger, it's a horizontal stretch. Now, what happens if now horizontally you stretch it out? It gets wider. Now, here's where it gets confusing, because doing this and doing this has the same impact on the graph, right? Makes the graph wider. If the graph, because if, think about now the x-axis is elastic, and I stretch it out and pull it this way. It's stretching the axis and it's pulling. Think about silly putty. Have you ever played with silly putty before? So if you put it on the graph and then you stretched it this way, what's happening to the graph? It's starting to get wider, right? That's what I was saying. Is here's the funny thing about it. This and this have the same impact on the graph. So a vertical stretch could be defined as a horizontal shrink, and a vertical shrink could also be defined as a horizontal stretch. You could write them as the same thing. You could. So A is less than 1? Well, because it depends on, you'll see, we'll get to some that, yes. Now, when we do these one-on-one, one by one, just one transformation per time, it's pretty easy, it's pretty straightforward. We're going to get to where we combine them, and then we combine them. So what we're going to do today is start with triplets. Tomorrow we will move into dilation, and then Thursday we will put all three all together. Now, this is going to feel like a lot, and this is a lot, but it's an entire package that you're going to have a part of it due each time. Take one back. Number 2. Yes. We should have no problemo getting this done. Oh, I might have got that for you. You could ask. I know some. That's very true. Is that your coach?
But we need study hall back. Study hall was so nice. I actually got work done. Like after them polls.
Well, you're probably one of the reasons they don't have it anymore, Charlie.
Yeah, well, I mean, most time I didn't have anything. We had study hall like last night.
Yeah, study hall was pointless our freshman year because our work was easy. Like,
Now I need it.
now I need it. Like, after them polls, it'd be like I finally start work at like 10 o'clock and just unmotivated by that. Oh, I know.
Well, it's too late to start homework. I'll be going to bed at 10 o'clock.
That's what I'm saying. I'm just like, a bump that I just do it in Spanish class. And it's why we yelling at me.
Well, why don't you use your time today to do it in here, and then you'll be.
I'll try.
Yeah, I'm doing art. Well, I just do it. I'll do it.
All right, let's look at number 2 together. 2 is a what? What's the parent function there? Quadratic, but give me the equation. That's right.
Oh, good job, kids.
Anybody confused? Look at the shape of the graph. Determine what the parent function is. All right, next thing it says, what transformations happen? And look, this is just slides. That's all this is going to be. Up, down, left, right. Today. Show it went. Hold on, we're getting there. We're getting there. Charlie, tell them again what the transformations are. What happened? Right 3, down 1. Does everybody agree? Look at that graph, right? That quadratic, the parent looks like this, 0, 0, 1, 1, and this one looks like this. It looks like it went right 3 and down 1. Is everybody okay there? Now it asks for the equation. Well, if I slid it right 3, what did I do? Subtracted 3 from the x, right? Everything else stays. So that's going to be f of x equals x minus 3 squared. It has to stay inside the parentheses like that. And then how do I say down 1? Minus 1.
I did do it right. That's so
okay. The domain and ranges of the new graph that you just did. Okay, so look at the graph here. What's the domain? I'm not done. I thought I was going to be. It's going to be a little more than 4. Okay. Yes or no?
That's hard.
How about domain? Look at your graph. What's the domain? Negative infinity to infinity. No matter how you slide these graphs, that should be your domain, period, for every one of them. The range is the only thing that's going to be a little different. What's the range? There you go. No. What are you doing? All right, flip it over. Three different ways we are doing this. Oh, yeah, was it on there? I'm sorry. What's the vertex? Three, negative one. Say that one more time. Yes. Slides are easy. Translations, I'm just easing y'all into it. All right. Now look at. Hey.
There's like no physical work, like steps. I can't do it. I'm like lost.
Look at numbers 4 through 9. Now we're going to go backwards on it. Instead of starting with the graph, we're going to start with the equation. Pick one of 4 through 9 you want me to work. Your choice.
6. Give me 6.
They don't get progressively harder if y'all are looking at it. So look at them and see which one.
6.
No,
Let's definitely do 8 or 9. Actually, yeah, 4.
All right, we'll do 9. I heard more people saying 9. Again with the quadratic, right? 9 is y equals x minus 2 squared minus 1. What is the parent function? X squared. F of x equals x squared. What transformations are happening to the parent function? Right to Charlie. All right. They want to know how. How did Charlie get it, or how is it right one down
How
here?
is everything?
All right. Domain. Range. -1 to infinity. So it asks for a graph down below. It might help you to graph it first and then do the domain and range. This would be, of course, slid. I have my parent. Some people like to graph the parent and then move it from the parent. Some of you can see it without doing that. It doesn't matter to me, however you want to do it. This is, we said right 2 and down 1. There you go. I am going to let you try on 10 and 11 because you only have 2 of those kinds, and I don't want to do them for you. But if you can do all the rest, you should be able to do 10 and 11. All right, again, eased you in. This is a light load tonight, okay? So, but make sure, okay, 1 through 11 is due tomorrow. You'll turn in a part of the packet every day.